Okay, welcome to maybe the fifth lecture of 435. Actually, give me a second. Let me close my door. Okay, so again, if you can turn on your videos, it'll be great. Guys, can you hear me?
Yes.
Yeah, okay. It would be great if you turn on your videos. I get to see the visuals. I get to see the expressions on the face and I can adapt. Thank you, Anthony, Haufan, Matthew. We'll continue with foundations in 434. But we're done with linear algebra. I mean, again, we scratched the surface, but we did most of what we would need. And then as time goes by, we'll build up a little bit more. But we'll move on to some basics of signals and systems, particularly Fourier transform today. And we'll continue with Fourier transforms next class, and then we'll move on to other stuff, okay? I hope you're working on the homework one on linear algebra. And there will be a MP machine problem, which would essentially be data visualization, understanding data from sensors on a smartphone. That MP would be coming out soon, so be on the lookout for it. Of course, there'll be emails posted. Any questions from last class where we were talking about eigenvalues, eigenvectors, and how eigen decomposition is essentially expressing a matrix A in another basis and that basis spans the space of A. And we said, look, when you think about one value, there are lots of applications of eigenvectors and lots of utilities. One of them is if you want to do a matrix multiplication A square X, right? You multiply the same matrix A on X multiple times, which is A square X. You can think of this as A times X, right? And instead of doing this multiplication n times for a to the power n of X, one easy way is you basically project the vector X into an eigenbasis of A, multiply that projected vector with lambda times n, and then you convert it back to the original basis of that matrix. Okay, so that is the value of eigen decomposition or converting things to eigenbasis. And I want to quickly give you a proof over here that A to the power nx is nothing but, or let's do it for A square X. A square X is nothing but A times X, and A times X is lambda X, right? So you can write that as A times S lambda S inverse X, right? You can write that as S lambda S inverse times S lambda S inverse X. And then you can do things like S which is equals S inverse S is nothing but identity. So you have this identity, this S inverse X, which is S lambda square S inverse X, which is essentially A square becomes S lambda. Actually, I can even write equals. Well, it becomes S square S inverse. Right? So you can repeat this thing for A to the power n, and that would become S. Okay. So that tells you how one of the utilities where once you project things to the eigenbasis, oh, you are in very good shape because now it's just a matter of scaling up the vector by the value lambda. Great. So we will end here. And any questions thus far? Very good. With that, let's now change gears. Oops. Hey. Okay, good. Oh, you can't see my screen now. That's interesting. Okay, good. Can you see my screen now? Yes, thank you.
Yes.
Okay, good. Okay, so today we are essentially going to look at a little bit at Fourier transforms, specifically discrete Fourier transforms. And the reason we are going to do this is foundational to many things that you do, not only in signal processing, but in data science, in machine learning, in sensing, robotics, many applications are underpinned by Fourier transforms. And even though many of you have seen Fourier transforms, oftentimes Fourier transforms are taught as here are a bunch of equations and a quick intuition. I would like to kind of talk about Fourier transform from a linear algebra perspective. And again, if you're familiar with it, I would say maybe I would still say maybe you want to pay attention because you might see certain perspective of Fourier transforms that you've not seen in the past. Okay. So yes, this is going to be something that you are familiar with, but still give it a shot and pay attention to see if there's some value. I feel you might pull out some value from it. Okay. Okay. Let's get started. Very good. Okay. So let's take a signal, okay, which looks like this. Any random signal. Okay, let's say this is your voice which says hello, right? This is your voice signal, the voltage of your voice. And x-axis is time and y-axis is the signal amplitude or even the voltage. Okay, and time moves t0, t1, t2. And suppose you sample this signal at each of these times. So at time 0, you have this sample. At time 1, you have this sample. Time 2, you have this sample. Time 3, you have that sample, and so on, till time n minus 2, and then finally time n minus 1. Okay? So you have an analog sample, which is your voice coming out, but you sample the signal at your microphone. Can we get these notes prior? Yes, I will make. Today, I think it's too late. I should have done that. Today, I think it's too late, but you'll definitely get it after I'm done filling it up. But I will make it available prior. So you can also take down notes with me. Yes, thanks. Great. So as the voice signal comes out of your mouth, which is this red signal, this is what is coming out of your mouth. Your microphone is a digital device, and your microphone essentially samples this signal and records the values at different time instants. Okay. So what your microphone records is essentially a digital signal, which means you can basically delete the analog signal, and what you have are these digital values. Oops. What you have are these digital values. In fact, maybe we should put one negative as well. T4, you have a negative value. Maybe T5, you have another negative value, and then again it goes up. Right? Very good. Now these values that you have, let's call them x0, x1, x2, x3, and so on till xn minus 1, sorry, xn minus 2, and xn minus 1. Trivial. Now, all these values, this is x4, all these values of x1, x2, x3 till xn minus 1, that is the digital signal. Do you agree? So then I can write a digital signal as a vector. So I'll write this signal as x as a vector, and then that vector would be x0, x1, x2, blah, 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 xn minus 1 transpose. Make sense? Transpose, because whenever we say vector, we think of it as a column, but because we wrote this as a row, we are going to transpose it. Very good. So now we are ready to think of signals as a vector. And any signal, if you take n samples of it, it will be some vector. In what dimensional space will this vector lie? If I say x bar belongs to R what? Someone?
Rn.
Rn. Okay. So this is a vector in Rn. So imagine this pencil is a n-dimensional vector. This is my voice saying hello. Your voice might be hello. That vector will change. Someone else's voice is hello. That vector will change. But it's just an n-dimensional vector. Whoever says hello in whatever way, that vector will just change. Because the x0, x1, x2 till xn value, only those values will change, but it will remain an n-dimensional vector. Good.
N is the total number of samples.
N is the total number of samples that you have taken. You can choose n, right? If you choose more n, maybe you are going to say, hello, how are you? Or you are going to sample it faster. So you'll still have hello, but you'll have more nicer resolution signal, right? It will be fine-grained. So you have a choice on n, but let's not worry about n. Let's take n as some given value right now. Very good. So then x is an n-dimensional vector. Now, if I ask you, hey, x is an n-dimensional vector, but what are the dimensions in which you're expressing x? Means this x0, on what axis do I say x0? On what axis should I have x1, x2, and so on? So look, if you think about it, this vector x is actually in a reference frame, in a coordinate frame, which is made up of this time t0, t1, t2, t3, and so on. Meaning the coordinate framework or the basis in which you're expressing this x is time t0, time t1, time t2, all the way till time n minus 1. Now, look, x is nothing but a projection on t0, and that will be x0. The projection of x on t1 will be x1. The projection of x on t2 will be x2, so on. The projection of x on tn minus 1 will be xn minus 1. Are you completely with me? Right? So because remember we said x0 is what? The value of the voltage at time t0. So now you make the time t0 of a dimensional vector. In the time t0 dimension, I have x0. In the time t1 dimension, I have x1. Then the vector x is nothing but x0 times the t0 dimensional vector plus x1 times the t1 dimensional vector, and so on. Right? So then now let's make everything mathematical. So this t0 vector, which is one of the dimensions or one of the axes, how do we write that axis? Oh, nothing but t0 is nothing but 1, 0, 0, 0, 0, 0. T1 is nothing but 0, 1, 0, 0, 0, 0. Someone tell me what Tn minus 1 is? Guys?
Is it the last time increment?
Yeah, but what should I write? The Tn minus 1 axis, how should I write it as a vector?
0 n times and then a 1.
0, n minus 1, n minus 2 times, and then there is a 1. Sorry, 0, n minus 1 times, and then there is a 1. Perfect. Okay.
Yep. Is this all we've covered? Because I had trouble logging onto Zoom because of the new policy change. I just wondering, is this all you've
Yes,
talked?
this is the first page. So there's nothing before this.
Okay, thanks.
Okay. So I hope this part is completely clear that this vector x, the signal vector, the hello, is in a basis, and I know what are the axes of this basis. I know the axis vectors of this basis, right? So now then we can write x, this signal x, as x0 times this vector is t0 plus x1, this vector is t1 plus all the way till xn minus 1. 1 second. Times this vector is t n minus 1. Are you with me? Right? If you look at it, if you do this addition, it will exactly become x0, x1, x2, xn minus 1. Just do the right hand side addition. Every vector will, at every point x0, then it will be x1, then it will be x2, then it will be xn, so on, xn minus 1. Right? So now we can write this even more nicely. We can put t0 over here. We can put t1 over here. All the way we can put tn minus 1 over here. And someone tell me what should be over here. I can write this as a matrix multiplication. So what should I write here?
Is it x0 to xn minus 1?
Perfect.
Also, what's the meaning of the power to the capital of T on the first page?
Say that again.
Why did you put on capital T there on the first page?
Oh, this one?
Yeah.
Oh, that's a transpose. Anytime we think of a vector, we think of the vector as this.
Okay. All right. Got it. Thanks.
0, x1, right? Blah. Good. So I can now write this x vector as some basis matrix, right? These are basis vectors. You agree? And this is the signal. In other words, this vector of hello is essentially a vector that is expressed in some basis. And in this time case, this basis happens to be an identity matrix. Right? So this basis vectors, this is called the time basis. Because you created these bases out of time, right? T0 is, if you think of T0, it is nothing but 1, but all the other times are 0. If you think of T1, this is nothing but T0 is 0, T1 is 1, and everything else is 0. Right? So this is called the time basis. And you're expressing your signal as a multiplication with the time basis. Please tell me if this is not clear. Very good. Okay. Now, I want to ask this question. Is basis for a space unique? Guys?
No.
Not at all, right? Imagine the 3D basis. My 3 fingers form a basis. By the way, if I have the 3 fingers like this, first of all, this is a basis. This is a 3D basis. Even if I make them like this, like they're in a they're like a pyramid, the edges of a pyramid. Is that a 3D basis? Sure, right? They are linearly independent, so there are 3D bases, right? So here is a 3D basis. If I rotate it, it's a 3D basis. If I move them, it's a 3D basis. There are many 3D bases possible, right? So this time happens to be one of the 3D bases for these n dimensions. But suppose I think of another 3D basis, and let's call that 3D basis F, just for the lack of a better word or lack of a better letter. Let's call that 3D basis F0, F1, F2, all the way till Fn minus 1. And this is some other basis. Okay. So now if you take that same hello, if you take that same hello signal and you represent in this new basis, we will obviously have different values, because once you project x to F0, let's say the value becomes Z0. When you project x to F1, let's say the value becomes Z1. On F2, the value becomes Z2, and so on. The value becomes Zn minus 1. Right? Wouldn't 3 vector, I'm looking at the chat message. Lucas, feel free to just unmute yourself and speak, because I might miss chat messages.
So the pyramid isn't each pair of 2 vectors next to each other like on the same kind of tilted surface, or am I thinking about it wrong?
Oh, let's quickly look. Pyramid, right? So if you look at this vector, and this vector, right? These two form a surface. These two form another surface, and these two form another surface. So these are linearly independent, because you cannot make the third vector out of a combination of the 2 other vectors.
Ah, I see. So they would all 3 have to be on the same.
They all, if instead of this vector, if this vector was on this plane, right, on this plane, then it would be linearly dependent.
I see. Okay, so they all need. So it doesn't matter if 2 are linearly.
Of course, 2 will always be on the same surface, but linearly independent means the 2 are linearly. These two are linearly independent means you cannot make this vector with that vector. If you scale this vector up and down, you will not be able to make this vector. Right? So these 2 are linearly independent. Now, if you take a third one, you cannot make this third vector by a combination of these 2. And by combination, we mean W1C1 or W1V1 plus W2V2.
Okay.
That's what we mean by a
You would
combination.
not be able to make any combination or any of them with a combination of the other ones. Okay, thank you.
Perfect. Good. Okay. So now I have taken that same hello signal, and now I am expressing it in a different basis, which is the F basis. Okay. So then if the projections of X on these F bases are Z0, Z1, Z2, so on, then I can write this vector X as F0, F1, blah, 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 Fn minus 1. And let's call this the X vector in the F basis. Right? So this one, let's go back and call the X vector in the T basis. Right? Where this X vector in the T basis was X0, X1, so on till Xn minus 1. And now in the F basis, that became, actually, let's not do it. This is not F0, F1. Sorry, you should have corrected me. This is Z0, Z1, Zn minus 1. Tell me if that makes sense. This vector projects to x0, x1, x2, xn minus 1 on the time basis. The same vector projects to z0, z1, z2 on the f basis, on a different basis. You change the basis, your projections will become different. Very good. So then we can write xf as, again, similar to above, f0, f1, f2, so on till fn minus 1 times what? What should I write here?
xf
Huh?
d0 to the d0 to the n minus 1.
Exactly, right? z0, z1, so on till z n minus 1. Make sense? Well, this basically is some other basis. And this is the signal, or let's call it the same signal in this other basis. Are you completely with me? I haven't said anything non-trivial thus far, right? I have taken that same hello signal and just shown it in two different bases. Very good. So then can we write I times xt? Okay, you tell me, I times xt, this is the hello signal, hello, is the same as, let's call this matrix F. What can I write here on the right hand side of this equation?
F times some other matrix times the signal.
F times some other vector,
Another
right?
Vector.
And that vector is nothing but xf, right? Because look, this is xf. And this vector is exactly this vector.
That's sufficient? You don't need to do any other transformation?
Why? Because this x is exactly, when expressed in the time basis, you have this xt. When expressed in the f basis, you have xf.
Oh, that's kind of nice.
Right? Very good.
Wait, what's the point of putting I there?
There's no point. I'm just explicitly saying that it's in the I basis.
Okay.
Right? In fact, whenever you think of a vector x, right? Whenever you think of or let's say a vector v, where let's say v equals v0, v1, v2, you are essentially saying this vector v is in the I basis, right? Because this vector v is actually v0, v1, v2, right? We typically don't say the I basis, but it's implied, right? So that's why we are just putting it over here just to imply that the xt part is in the I basis, the identity matrix basis.
Yeah, that makes sense.
Okay. So we have come to this point, and when we are saying there is some basis f, we can take any basis, and if we express the same signal in that basis, it will look different. But we can always write this equation: ix equals f, ixt equals f xf. Okay. Same signal expressed in the time basis, same signal expressed in the frequency basis. Okay. Now we are going to look at what we call, or we are going to look at some interesting basis that Fourier came up with. Okay. So now we are going to reset and we are going to look at something completely different. So I want you to kind of shelf all of this that we've talked thus far, clean the slate of inside your brain, clean the blackboard inside your brain, and we are now going to look at something completely different, and then we are going to come back and connect everything. So what we are going to look at is rotation. Okay. So, when humans were basically developing math, right? Math is essentially a language. I hope you all agree. There is English, there is French, there is Hindi, there is Java, there is Python, and there is math. They're all the same, right? You see 2 trees, 3 elephants, 5 houses. There is no number 2, number 5, number 3 in the world. You just made it up, right? It's human imagination that you made it up, and that became the language in which you express certain things, and that is math. No different from English, no different from Java, Python. You're expressing certain concepts. So when humans are developing math, one of the things they thought was, okay, I have numbers. Can I start to also mathematically express the notion of rotation? Okay. So what does that mean? That means imagine there is a stick and the stick is rotating. Maybe this is at the invention of the wheel. People are thinking, oh, wow, look at this. This thing can spin. How do I mathematically say this? Okay. So I want you to think about how we can express a stick that's rotating in math. I cannot say a stick. Yeah, you have to say it mathematically. So one way, let's assume trigonometry has been invented by now. Okay. Then one can say, look, the stick is over here, and then after a time, the stick has moved, rotated an angle theta. So at t0, at time t0, the stick is here. And let's say the size of the stick is 1. So at time t0, I can express the stick as 1. At time t1, I can express the stick as cos theta plus in the perpendicular direction sine theta. Do you agree? Right? In the perpendicular direction, I have sine theta, and in the horizontal direction, I have cos theta, and I express the first position of the stick as cos theta plus in some perpendicular direction sine theta. This is still not math, because this notation that I have used is just an expression. It's still not mathematical. There's no notation like this. But let's keep going forward. Let's say at time t2, you have the stick is over here, which is 2 theta. So I can express that as cos 2 theta plus in the perpendicular direction sine 2 theta. And I can keep going like this, and I have t of n minus 1. I can say cos n minus 1 theta plus in the perpendicular direction sine n minus 1 theta. And that theta would be this. Oops. Are you all with me? I'm starting to model express rotation mathematically. Okay, very good. Now, humans thought, okay, so how should I, so this is still not mathematics, because even though this is fine, this came from trigonometry, this came from trigonometry, what do I do with this? I have a way of expressing rotation, but I'm still not there. So you know what humans did? Humans said, we'll do what we always do. We'll just make up stuff. So we will say, let's define and let's give a character J to what we call a rotation of 90 degrees. Okay. So instead of saying this as perpendicular, in the perpendicular direction, this means in the perpendicular direction, we are just going to call that as cos theta plus j sine theta. We're just going to make it up. Okay. If you tell me, hey, what are you doing? Hey, Romit, you're just making up things for math, right? Here is my answer to you. Negative numbers is completely made up. Imagine humans first created number systems starting from 1, 2, 3, all the way till, let's say, 100. Then they invented 0. Then they said, okay, here is 0. And then they said, you know what? Let's make up negative numbers, which goes this way, which is -1, and we'll just put a dash in front of that number. The dash is just a made up character. And we'll say -1, -2, -3, so on. There is no such thing as -5 elephants. There's no such thing as -$2. We just completely made it up. And we said, we will think about this negative number and we will express that by putting a minus in front. And we'll go in the opposite direction of plus. But in all our math, you owe me $5, I owe him $13, he owes you $7. And in this debit credit system, we will model those debit and credit by plus and minus numbers. And eventually things will cancel out and everything will make sense, because in reality, there are only positive numbers. $5, $7. Right? But in doing all this calculation, internally, there are negative numbers in it. Completely a figment of your imagination. Right? So my point is, this axis is still physically understandable, but this axis is completely made up. And you put a minus sign on top of it, it's completely made up. There is nothing as -3 dogs or -3 laptops. If you're fine with that, then I would submit, what is your problem in making up another axis, which is J? And this axis would be a 90-degree counterclockwise rotation. I'll just make it up. So then I can express this vector stick as some cos theta in this direction. By the way, this is 90 degrees. And some sine theta in the j direction. If you're fine with that now, then I would say this is totally fine. Cos theta plus j sine theta, where j is a 90-degree rotation, counterclockwise. I have made it up completely. But if you tell me how can you made it up, I would say you made up negative numbers. So you cannot argue with me anymore. Okay? But in making up negative numbers, we said one thing. We said, look, if +2 goes in positive and -2 goes in negative, then when you add up, they become 0. Right? I give that constraint. I think this -2 means when you add it with +2, it should become 0. So you want to kind of constrain or make some axioms of our definitions, right? So we can now say, okay, what about j? We say, look, if I make j times 1, that means my vector gets rotated counterclockwise once. Now, if I take that vector, which is rotated counterclockwise once and becomes vertical, right? This is a vector 1. Let me do this here. This is a vector 1. If I do a j operation on this, this is what it becomes. Now, if I do a j operation on that once again, what should it become? What should that vector become? It becomes j.
-1. No.
It should become -1 because you give another rotation, right? So this becomes -1, which means j squared is basically -1. This is my constraint. I'm not doing something arbitrary. I started with something arbitrary, but I'm constraining it to make meaning. So that means I said j is nothing but square root of -1. What does that mean? God knows. But I don't care, right? Because as long as I am consistent with my definitions, I'm fine. Right? So this becomes complex numbers. Mathematicians couldn't say what it means physically, but I don't care. In my intermediate steps, I will use this because it's my imagination. But at the end, when the results come out, everything will make sense and nothing will have square root of -1 in it. If you're fine thus far, then I would say I can define all of these as 1 plus j0, this as cos 2 theta plus j sine 2 theta, so on cos n minus 1 theta plus j sine n minus 1 theta. Cool so far? I have started to model rotation. And then the Euler came and said, look, this can be expressed nicely as e to the power j0, e to the power j theta, e to the power j2 theta, so on till e to the power j n minus 1 theta. Questions, guys? Oops. All right. All right so far. Very good. So now we are back to business. I can express rotation as this, and this is a vector. Okay. So now I can do the following. I can say a rotation is nothing but e to the power j0, e to the power j theta, e to the power j2 theta, all the way to e to the power j n minus 1 theta transpose. Are you with me? Look, this is the beauty of mathematics, right? I've taken some physical phenomena, I put in my own imagination, my own way to express it. I made sure I do not say something arbitrary. I gave some boundary conditions to my imagination, right? Some consistency. And then I bring it down to something that I know, which is vectors. So a rotation of a stick, I think we can even say a rotation of a stick of length 1 is this. Okay. If the stick was length L, what would have happened to this vector?
Be scaled up.
Just scale it up with L, because this would have been L cos theta plus perpendicular L sine theta, which would have been L cos theta plus j times L sine theta, and that would have been L times e to the power j theta. So this would have been L times this vector. Oh, that means we are even better. We don't care about the length of the stick, because whatever the length, we'll just multiply that length with that vector. So cool. Very good. So I have expressed rotation where the rotation took n time steps to complete one cycle. I've expressed that rotation as a vector. Do you agree that this rotation took n steps to complete one cycle? This is where I want you to start paying attention if you're kind of casual thus far. Now, I want to become a little bit more ambitious. Now I want to say, okay, you've done a good job, but how can you now express faster rotating sticks? What you've expressed thus far is some speed of rotation which completes one full cycle in n steps. 0, 1, 2, 3, 4, all the way to n minus 1. But can you model a stick that is faster or twice as fast? So sure, the answer is sure, I can do it. Right? So look at this. Now I want to model different speeds or frequencies of rotation. And I know that one cycle per n time units, this I already know is e to the power j theta, e to the power j2 theta, so on. Now, suppose I ask you, what would that vector rotation be, or what would that vector be if instead of one full cycle in n steps, I complete 2 full cycle in n steps? Meaning, I have this stick, instead of going, I have this stick, instead of going one full cycle, I want to go 2 full cycles. In n steps. Can someone tell me what should that vector be?
Could you replace all of the thetas with a theta twice as large?
Perfect. Perfect. Because to double my speed of rotation, every time I took theta jump, I should now take 2 theta jump. That'll just make it happen, right? So then I should start off with e to the power j0 because that's my starting point. Then I should do e to the power j2 theta, e to the power j 2 times 2 theta, e to the power j 3 times 2 theta, so on, e to the power j n minus 1 times 2 theta. Are you with me? Very good. Now I tell you, let me make this stick rotate really fast. Okay. N minus 1 cycles per n time steps. Here you are doing 1 cycle per n time steps. Now I say n minus 1 cycles per n time steps. It's finishing n minus 1 rotations in n time steps. What should this vector look like?
Do you scale it by e to the n minus 1?
You scale the theta by n minus 1 theta. Okay, so e to the power j0. The first one is e to the power j0, right? Because the stick starts at a horizontal position, right? Then it's e to the power j n minus 1 theta, because that's where the stick goes the first time. Then it's e to the power j twice n minus 1 theta, e to the power j thrice n minus 1 theta. And where does it end, guys?
And squared.
Huh?
Go ahead.
Go ahead.
Sorry, n minus 1 squared.
N minus 1 squared. Okay. You have now modeled sticks rotating at different speeds, where the speeds are double, triple, quadruple, so on till n minus 1 of a basic speed, which was 1 cycle in n time units. Is that totally clear?
Professor, could this
Yes.
be written more simply by just multiplying by the scalar?
Multiplying which with the scalar?
The vector, like the vector on the left by e to the n minus 1?
Hey, if you multiply a vector e to the power x with e to the power y, it's not e to the power xy, right?
No, wait. Okay. Isn't e to the n minus 1 a scalar though?
What, e to the power n minus 1?
Yeah.
Huh?
Is that not a scalar? It's just an arbitrary number. Like, say n minus 1 was like 5. So it'd be e to the 5. Wouldn't that just be a scalar?
It would be a complex number.
Which would be
Yeah, it would be a scalar in the complex plane. Yeah.
So if you wrote next to the one cycle vector, e to the 5,
Right.
that would just mean you're multiplying each term by e to the 5, right? So that wouldn't that just be a simpler way to write?
No, but e to the power x times e to the power y is e to the power x plus y, right?
Yes. Oh, whoops, I see.
Yes.
My bad.
Yes, that's fine. I know many of you are rusty, so this is also, I know these are, you know these, you knew these like the back of your hand. Over time, I know things get rusty. Totally fine, totally fine. But please ask questions. Don't stop yourself from asking at all. Very good. Last question I want to ask you is, what is the slowest frequency of the stick? The slowest frequency is when the stick is not moving. Right? I mean, that is also like moving with zero value, zero speed. Right? So if I say the stick is moving with 0 cycles per n units, in other words, not moving at all, how would you model that rotation? The stick is not moving at all. So at time 1, it is there. Time 2, or time 0, it is there. It is in the horizontal position. Time 1, it is in the horizontal position. Time 2, it is in the horizontal position. It's not moving at all. The frequency is 0. Then what should that vector be?
Should be 1, right? Because we're raising it to the 0 power.
Correct. So it's e to the power j0, e to the power j0, e to the power j0, blah, 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 e to the power j0. Does that make sense? Guys,
Is it
now,
vector a basis?
say that again.
Is it
Wait, yes,
vector-
John, wait. I am about to, this is my climax point, okay?
Oh, I'm sorry.
Yeah, don't take my thunder away. Okay. So thus far, now you've done something interesting. You have not only modeled rotation as a mathematical vector, you've even been able to model the frequency of rotation as different vectors that has some nice structure. Right? Let's call this vector F0, F1, F2, Fn-1, simply because they're rotating at frequency F0, which is 0 cycles per n time steps, frequency F1 at 1 cycle per time step, the stick is rotating at F2, 2 cycles per time steps, and so on. Okay. Each of these vectors are n-dimensional vectors. You agree? Good. Fourier, this is where he made this absolutely breathtaking observation. He said that vectors corresponding to Fi and Fj, I not equal to j, are orthogonal Can you believe that? Each of these vectors, you take any pair of these vectors, this one and this one, this one and this one, this one and this one, any pair of those n vectors, they're orthogonal. Right? That was absolutely breathtaking. Right? Your stick is rotating at different frequencies where the frequencies are integer multiples of each other. And if you think of that rotation at certain frequency and that rotation is at another frequency, and you take them as vectors and you do a dot product of them, they become 0. Whoa. Right? One way to see this intuition is, let's take this one and this one, F0 and F1. F0 is nothing but 1, 1, 1, 1, 1. Right? So if you take the dot product of F0 with F1, it is like adding up all the values of F1. Do you agree? Because dot product of 1, 1, 1, 1, 1 with this e to the power j0, e to the power j theta, blah, 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 e to the power j n minus 1 theta. This dot product is nothing but taking this multiplying with this, plus taking this multiplying with this, plus taking this multiplying with this, and so on. So this is all adding all of these up, because multiplying 1 with each of these will just give that. So now the question is, why is e to the power j theta? Okay, maybe you should write this. E to the power j theta plus e to the power j2 theta plus e to the power j3 theta, so on, e to the power j n minus 1 theta. Why is this equal to 0? Well, look at it, why this should be equal to 0. Let's go back to that rotation. Look, this rotation is going to be like this. E to the power j0, e to the power j theta. Let's take 45 degrees for now. E to the power j0, e to the power j45, e to the power j90. This is e to the power j n minus 1 theta. Remember, theta is 2 pi by n. Okay. So now you add these things up. Well, this cancels with this. This cancels with this. This cancels with this. This cancels with this. You have 0. So at least you have proved that F0 and F1 cancel with each other. Right? You might want to prove by yourself, take any pair, take F1 and F2, and see if you can prove that they will cancel each other and become 0. The dot product will become 0. I shouldn't say cancel with each other. You have to, this dot product is a little bit more complicated, because you have ej0, ej theta, so on, multiplied by this ej0, ej2 theta, ej4 theta, and so on. But you can try it yourself to see why it becomes 0. Very good. Any questions thus far?
Hey, Professor, so you're saying the 0 cycles times the 1 cycles equal 0 still, and the 1 cycle times 2 cycle vectors are 0 as well?
If any 2 cycles, if you take their dot product, it will be 0.
Okay.
Right. Another quick observation I want to make is, yeah, maybe it's a good time to make this observation. Guys, can you imagine this rotation, what it looks like? This rotation looks like I'm going to just write it here and then make it very small. This is e to the power j0, e to the power j n minus 1 theta, e to the power j 2n minus 1 theta, so on, e to the power j n minus 1 square theta. This is basically n minus 1 cycles per n time steps. Are you with me? This is the same as this one. Correct? Now look at what this looks like. This looks like a stick which started at e to the power j0. What is the next time step? Where does it go in the next time step? Someone?
It goes down 1.
Exactly. It goes n minus 1 theta over here. Right? This is e to the power j. So this is at time 0. This is e to the power j n minus 1 theta, which is at time 1. What happens in the next time step?
It goes 1 back again.
It goes
Does this have anything to do with something like aliasing?
no. But this has something to do with what we think about as negative frequencies. Guys, do you see that now, if you think of this stick, it's spinning very fast, but if you're looking at that stick, at a certain interval, the stick will actually go backwards, right? So in some sense, if you think of this as negative frequency, the stick is rotating in some frequency, but you now say, okay, how can I think about negative frequency? Well, negative frequency is nothing but really high frequency. Because at really high frequency, the stick will start going backwards. If you sample it at a particular, yes, it has connections to aliasing, but in a very indirect way. For now, just think of when you go very fast, you go backwards. Right? So now the stick is going this way. And this is one way to visualize what is negative frequency, but we'll come to that later. I just want you to get a visualization of what this means.
Hey, Professor, is that why if we see a wheel moving really fast, it looks like it's moving backwards sometimes?
Exactly. Because your
And this-
camera or your eye's refresh rate is this sampling rate, and it's actually going backwards. It feels like it's going backwards.
Okay.
So
And
now
could you
you can
also
also-
explain?
Yeah, go
Could you
ahead.
explain that dot bubble, please? What do you mean by that?
Which one? Which one?
The vectors corresponding to Fi and Fj are orthogonal.
Oh, this is a vector. This is another vector. This is another vector, and there are n such vectors starting from f0 to fn minus 1. You take any of those two vectors. When I say fi not equals fj, it means that you pick two vectors, but you cannot pick the same vector twice, right? I'm saying I not equal to j, meaning you cannot pick f1 and f1. I and j have to be different. So you pick f1 and f5, you pick f2 and f7, whatever you want, but I and j have to be different. The dot product of those two are orthogonal, meaning those two are perpendicular vectors.
So because the dot product 0, that means they have to be perpendicular.
We said that last class, right? Dot product 0 means they are perpendicular. It's an if and only if, right? So if it's dot product 0, they're perpendicular. If they're perpendicular, their dot product is 0.
Got it. Okay, thanks.
Good. Okay. So now you can easily see another proof. You can prove yourself that this times this dot product is also 0, because it's now that same stick moving backwards, and if you take n such values, it will be this, and that they'll all again cancel each other. And that will become 0. Very good. Let me resize this, cut it, and put it next to here so that you can always visualize this over here. In case you want to see that later. Very good. So this was Fourier. One of my most favorite scientists, and he made this observation. Okay. So now look, these Fi vectors are n-dimensional vectors, and f0 to fn minus 1 are all orthogonal. Okay. If they're orthogonal, they also must be, if they're orthogonal, are they linearly independent or they're linearly dependent? Someone, come on.
If they're orthogonal, they have to be independent.
They're orthogonal, they have to be linearly independent. So they're also linearly independent. Very good. If they're linearly independent, these vectors will have to form a dash for n-dimensional space. Huh? Yes, go ahead.
A basis?
Basis. For n-dimensional space. Happy? So if they form a basis, then we can go back to our earlier equation. This one. And we can plug those F vectors in this basis. Basically in this basis. And not only it's just a basis, it's an orthogonal basis. So it's the best kind of basis that I would love to have. Right? So then what I do is I say IXT is F XF, that same equation, where F is nothing but F0, F1, so on, Fn minus 1. Right? This is the same F0, F1, Fn minus 1 from here. From here. This is F0, F1, F2, so on. I just plug those vectors into this matrix here.
Professor, so you're saying that each F0 or F1, they're each independent vectors?
Not only independent, they're orthogonal because Fourier said that. Fourier showed that.
Yeah, so they're orthogonal to each other.
Correct. And therefore they're linearly independent, therefore they form
Yeah.
basis.
So when you say that they're or could you go up a little bit? When you say that F0, F1, like they're all n-dimensional, does that mean like, you know, they're n time steps?
Yes.
Okay.
These vectors are n-dimensional because there are n values right here.
Okay.
Starts from 0, ends at n minus 1.
Okay. Gotcha. Okay. So if we just pick an arbitrary n, like, so you have to say if there's 17, so if there's 17 dimensions and they're all orthogonal to each other.
Right.
And that's impossible to visualize, right?
Yeah, it's hard. I mean, you have to think of a 17-dimensional vector.
Yeah.
And because this is 17-dimensional space, you can have 17 different vectors that are all orthogonal to each other.
Okay. And they're all, okay, got it. Thanks.
Okay. So now this XF is now what we called as Z0, Z1, so on till Zn minus 1. Do you agree? Very good. I think we are in business. Again, this is the time basis. This is time domain signal. This is the frequency basis, also known as the Fourier basis. And this is what is called Fourier transform, or frequency domain signal. Hey, Fourier transform is no big deal. It's just saying I take that signal and I basically express it in a different basis, where the basis vectors are actually rotations of different speeds. That's all. Okay. Thus, Fourier transform is the representation of a signal vector in a different basis, and that different basis happens to model rotations at different frequencies. If you're happy with that, then I can now write mathematically the same equation over here, IXT. Let me move this a little bit. IXT equals FXF. That implies IXT is basically XT. So FXF equals XT. Okay. So XF, this one, is basically F inverse xt. Simple, right? Guys, this is also where you want to pay attention. F inverse xt. It turns out there's a property which says if you have an orthogonal matrix, the inverse of that is nothing but the conjugate transpose. Okay? This is a property. If you feel like, look up how that happens. But this can be written as F conjugate transpose. This is just a plain linear algebra, and maybe I could have given this for your homework. It's not very hard to prove. F inverse for an orthogonal matrix is F conjugate transpose times xt. Okay. So then what is F conjugate transpose? I am going to do transpose of each of the columns of F0, F1, F2, and then conjugate it. So the columns that were F0, F1 will now become rows. Sorry. What should be here, guys, in this vector? What should be here?
x0 to xn minus 1.
Agreed? So now, and what is this xf? This xf is nothing but z0, z1, zn minus 1. Guys, is this clear? Very good. So now I want you to do this. Z0 is this row multiplied by this column, right? Z1 is the second row multiplied by this column vector, right? So I want you to tell me what is Z2. Just write it out. Z2 is basically the third row multiplied by x0. So the first term is e to the power minus j0 times x0 plus what? Someone? This is the third row, which is basically the third, which is basically F2. F2 conjugate, right? So if I go up F2 over here, look, what is F2? E to the power j0, e to the power j2 theta, e to the power j2 times 2 theta, and so on, right? So this will be e to the power minus j0 because it's conjugate times x0 plus e to the power, minus j2 theta times x1 plus someone, what's the next term?
E to the power minus j4 theta times x2. 2 times 2 theta.
Perfect. What is the last term?
Two times n minus 1 theta.
Are you happy? And I can do the same things for Z0, Z1, Z2, Z3, Z4, Zn minus 1. Okay, good. Now tell me, I want to write this whole thing, instead of this long expression, I want to write it as a sum. Can you tell me how should I write it as a sum? What am I multiplying xn with, where this small n is going from 0 to n minus 1?
a to the power minus j 2n theta.
Agree? Just make sure you see it. When n is 0, this is 0. So this is e to the power j0, which is this. When n is 1, this is 1. So e to the power minus j2 theta x1, which is this. N is 2. This is so this value is only changing. Actually, let me write this. This is actually, I don't want to write it this way. I want to rather write it. This is the right way to write it. The 2 theta is remaining constant. Let me even. Okay. And theta is how much? Right? 2 pi by n, remember? So that means now tell me, we did this for Z2. What now? Generalize it for Zm. Any of these vectors, Z0, Z1, Z2, Z3. For Zm, can you now rewrite this for any general M? I can get you started.
Replace the 2 theta with m theta.
Perfect. Any problems? Because remember, it was Z2, and that's why you had the 2 theta. If it was Z1, you would have had only theta over here, only theta. This would have gone away. If it was Z3, there would have been 3 theta here. If it is Zm, there is m theta here. So this is m theta for Zm. Well, theta is 2 pi by n. So let's write that as 2 pi by n. Remember, this n is small n, which is going from 0 to capital N minus 1. Okay? So let's just write the 2 pi n before m and n. So I'm going to just rewrite this as minus j 2 pi by n m times n. This is nothing but discrete Fourier transform. When you do this really fast, there are nice ways of doing it really, really fast, because as you can see, there is nice structure in this. There is similarity across these vectors. So you can do these things very fast, these operations, these additions and these multiplications. When you do them very fast, it's called FFT. Fast Fourier transform. Okay. Now, one more thing I want to say is, actually, I don't need to say that. If someone brings it up, I'll say it, but otherwise I don't need to say it. One question I want to ask you is, what is this M in Zm? What is the physical meaning of M in Zm?
Speed or frequency.
Speed or frequency of rotation. Perfect. Okay. Fourier transform is nothing but I have expressed the time domain signal in another basis, and the projected values on that basis essentially that vector, those projected values, is essentially what is the Fourier transform of a signal. Questions?
Sorry, could you just explain like a little more the meaning of ZM? I've learned DFTs and FFTs, so I think I understand, like I thought I understood what they mean in the frequency domain, but it's just like I'm struggling to understand ZM. Could you explain that again?
Let's go back to the previous first picture that we drew. We took a signal like this, right? That signal we expressed as a vector. These x0, x1, x2, x3, so on, we expressed as a vector. That vector looked like this in the time domain, where the time domain axes were t0, t1, t2, all the way till tn minus 1. So we said this vector x, which is this signal, is essentially the time basis I multiplied by the vector x. But we said, look, the same vector x, if you express it in a different basis, then those signals, that same signal would become z0, z1, z2, all the way till zn minus 1.
I see. So could you think of Z as kind of like analogous to the actual, when you think of a plot on the frequency domain, would these be kind of like analogous to the Y values above a specific frequency?
Not above. I think you can even stop there. These are essentially the Y values in your FFT plot.
Okay. Okay. So they're kind of like the amplitude of frequency, kind of.
Yeah, exactly. We'll
Okay.
get to that. We'll get to that.
Okay.
But
Okay.
maybe because you brought up the word analogy, maybe here I have an analogy.
Okay. Okay.
Okay. You are a CEO of a company, or forget CEO. You know, we often try to evaluate the quality of a candidate in interview processes. Right? We interview them, we try to understand how good this candidate is, and accordingly give them a job or give them offer to grad school or give them offer to undergraduate college. All kinds of places we evaluate. So imagine this guy who is Albert. I'm not saying Einstein, I'm just saying Albert. Okay. And one way to evaluate Albert is in a basis where the bases are math, programming, and the quality of Albert's presentation, PowerPoint presentation. So basically this evaluates his communication skill, this evaluates his mathematical skill, this evaluates his programming / logic skills. That's one way to evaluate Albert. And let's say I give Albert scores of x0 in math, x1 in presentation, and x2 in programming. Right? Albert took a math test, got x0, took a programming test, got x2, did a PowerPoint presentation to an audience, and the audience gave him a score of x1. The same Albert could go to another company, and the other company said, no, we are not going to do math programming presentation. We are not going to do it that way. We have a different basis. And our basis is we are going to give a machine learning test. We are going to give a logic design test, and we are going to ask Albert to write a project report. Or we are going to ask Albert to write an essay. Machine learning is going to test math skills in a different way. Logic is going to test math skills, logical skills in a different way. And writing a report is going to test communication skills in a different way. And now Albert gets, in this new basis, in this new method of examination, Z0, Z1, Z2. Okay. My whole point is I can mathematically express Albert in two different bases. The first company's basis was math programming PPT, and in that Albert is a vector x0, x1, x2. In the second company, which is a Fourier basis company, which is a different basis vector, machine learning logic and written report. In that basis, again, this is Albert, but Albert is now a vector Z0, Z1, Z2. If the first company is, I don't know, I'm thinking of a company. Okay, forget it. Let's say Google. And the second company is SpaceX. X0, X1, X2 is Albert in the Google transform, in the Google basis. Z0, Z1, Z2 is Albert in the SpaceX basis. Right? And how do I get Z0 from X0? Haha, this is my expression. So this would be called the SpaceX transform. Assuming I is the Google transform, identity is the Google transform. Okay? So Fourier transform is nothing but looking at Albert through a Fourier basis, which is the SpaceX basis, which is machine learning logic and report. And the time domain version is looking at that same Albert in math project PowerPoint basis. Okay. So this brings us back to the last question, which is what is inverse DFT? Now, which means if you know Albert, if you know the Fourier transform, how do you get back to the time domain signal? Suppose I give you a signal in the Fourier domain, means I give you Albert in this domain. SpaceX tells, Elon Musk tells Sundar Pichai, hey, I have this really good candidate and his score is Z0, Z1, Z2. Google said Z0, Z1, Z2 doesn't mean anything for us. We need to convert it to Google basis. Basically, we need to get to X0, X1, X2 from Z0, Z1, Z2. How do I do that? Hey, that's not difficult at all. Assuming, remember, this Google transform has to be identity, right? So assuming Google transform is identity, then X0, X1, X2 is nothing but SpaceX basis times SpaceX vector, because this is identity. So I take the Fourier basis multiplied with the Fourier transform, and that's my X0, X1, X2. Make sense? So then look what inverse DFT is. IX, let's write this in the time. And actually let's write, hey, do you want me to write this as Z or do you want me to write this as XF? Where XF is Z0, Z1, Z2. Which one is more intuitive?
I think XF would be more intuitive.
XF would be more intuitive. I also think so. Yeah. So let's write this as XF. So now we are saying, I'm telling you that I have given you XF. Now you'd want to convert to time domain. What do you do? Oh, that's simple. You know what this Fourier domain is, the Fourier basis is. XT is nothing but IXT is nothing but XT, and XT is nothing but F times XF. So you basically multiply the Fourier basis, this one. This is X times XF. Right? And that would be, I don't know if you can visualize this, but you take this guy, this guy, this guy, this guy, this guy, and multiply with these guys, dot product. That would be X0. X1 would be the second guy here, the second guy here, the second guy here, and so on, and you multiply it with Z. That will be X1. So if you write this out, you'll see the following. I don't know if someone can tell me, Zm, where m goes to 0 to n minus 1, times e to the power j. Now there is no longer minus j because you're no longer doing conjugate and transpose. This is the original f. J to the power 2 pi by n mn. Actually, let me do nm.
Hi, Professor.
Yeah.
About the scalar 1 over square root of n.
Right. Yeah. So sorry. Let me not confuse people. First of all, let's take this as the inverse Fourier transform. This, Alan, I'll come back to your questions very quickly. This says that given the ZMs, I can get back xn. Okay. Given Albert in the SpaceX basis, I can get back Albert in the Google basis. Okay. Now there's one small change I'll make. If you look at these vectors, the length of the vector is more than 1. Is in fact square root of n. Why? What is the length of this vector? Remember, length is nothing but, if I give you a vector v, then length is vtv square root. Agreed? So if I take this vector and I take its transpose and I multiply it with the same vector, that vtv will become n, will be equal to n. Sorry, not small n. vtv will be capital N. Right? And length is nothing but square root of capital N.
Wait, could you repeat that? How is VTV equal to n?
Oh. Multiply. E to the power j0, e to the power j0, this is 1 times 1. Okay, I should say this. This is conjugate. Sorry. Now tell me. V transpose V for complex, you need to make this V conjugate transpose V. What we said V transpose V, we said it for real vectors. For complex vectors, you need to make it conjugate. Okay. So now you see, right? Everything becomes 1. So then it becomes n. Guys, is that clear? I don't know who asked that question.
It was me.
Yeah, Adil, is it clear now?
I'm sure it'll be clear when I work through it.
No. E to the power minus j times theta times e to the power j theta. How much is that?
It should be
E to the power 0. The exponents cancel off.
Oh, right, because it's addition, right.
Exactly. Right. So all of them will give you 1. And because dot product will add up all of them, you get n. So the length.
Okay. It makes sense.
Huh?
Got it. Yeah, it makes sense.
Good. Okay.
So transposing a complex vector makes it the conjugate?
No. When you take a dot product, okay, you have to, or when you compute the length of that vector, you basically conjugate and then transpose.
Why is that?
For a complex number, if you want to understand the length of that vector, you do a complex number.
Is it so it ends up back in real?
Say that again. Say that again.
The real as real numbers?
No, the way to think about it
Because
is
if you take the conjugate, it makes it
no.
real again.
You have a stick. This is e to the power j theta. Right?
Mhm.
This is e to the power minus j theta.
Yeah.
You want to basically cancel off the
J part.
the j part. Think about it, or if you want, hang back after the class. Okay. Very good.
Oh.
Okay. So where was I? So this gives us inverse Fourier transform. I don't know. I think I took a detour.
You were explaining why we had to multiply by 1 over square root of.
Oh, I was explaining why. Exactly. Okay. So as a result, I want the matrix to be not only orthogonal, but orthonormal. What does orthonormal means? Instead of having multiple vectors, I want the vectors to have length 1. It's like unit vectors. Okay. So I multiply basically this by 1 by square root of n. Then it becomes orthonormal. Okay. And as a result, I multiply all of this by 1 by square root of n.
It should be n, right? I mean, because when you multiply it by n times, it just cancels the.
No, basically this is basically a scalar. So as long as you do 1 by square root of n during FFT and 1 by square root of n when inverse FFT, you're fine. You can do
But in the formula it should be n.
But then the inverse FFT should not have n.
But no, I'm thinking the same as him. Do both have to multiply by 1 over square root of n, or only one of them?
Or you multiply only 1 by n.
Oh, right. Yes.
Right. Either you multiply only the FFT by 1 by n and don't do anything with the DFT, inverse FFT, or you do 1 by square root of n for both.
Wait, so you're saying converting, we only have to have 1 over square root of n on one of them? If you want to convert, like if you want to convert back, if I don't convert from like the z of m onwards, and I have to convert for x of n, right? Otherwise I can switch it.
No, all I'm saying is either you have 1 by n over here and nothing over here, or you have 1 by square root of n both while doing both. I like 1 by square root of n doing both because this essentially says that I'm basically dividing by the length, because the length of that f1 vector was 1 by square root of n.
Wait, so then if I'm converting back and forth, do I do 1 over square root of n both times? Essentially, what you're saying?
Yes, both times.
Oh, because then that will make it orthonormal. You're
Oh,
saying?
yeah, exactly. That'll make it.
Okay, got it. Thanks.
Okay. We will stop here and we will continue with FFTs a little bit more, but I hope this gives you some intuition to things that you've seen in the past, but you may not have seen it in this light. But also I hope this tells you what we were talking about last time, that IXT equals FXF. So if I want XF, I just basically take F inverse. Right? So remember our eigenvectors is S lambda S inverse. So AX is this times X. And if you think of this as S lambda S inverse of X, S inverse is an eigenbasis. So S inverse of X is basically converting X into a vector in the eigenbasis. Same as F inverse of XT is converting XT is converting xt to xf. Let me write this cleanly. Ixt equals fxf. This implies xf equals f inverse of xt. Right? That means what? I can now say that, oh, if you want xf, you have xt, you want xf in the Fourier basis. Then what do? You just take f inverse of xt. Whichever basis you want to go to, just multiply it with the inverse of that basis. So in this case, if I multiply x, which is in the time domain, which is in the identity basis, with S inverse, then I will take x from the identity basis to the eigenbasis. Right? So this vector is in the eigenbasis. It's like a Fourier transform, but it's like eigentransform. Now I multiply it with lambda. I extend the z0, z1, z2 values by lambda 1, lambda 2, lambda 3. And look, what did IDFT say? IDFT says, now just multiply with, now if you want to get back, just multiply with that basis f. Right? So then you just multiply this vector with the basis f. Okay. So I want you to go home and think about this connection, that if we think of Fourier transform as a change of basis, eigenvectors, eigen decomposition should also make sense through that lens, that it's a change of basis, just a different basis. One is a Fourier basis, the other is an eigenbasis. We will stop here, and I'm happy to hang back and take questions if you have any.
Yes, Romesh, I have a question.
Sure.
In your explanation, you assume that the samples in the frequency domain is the same as the number of samples in time domain.
Right.
They are all n, right? But I think it's normally in the practical case. I mean, when doing FFT, we normally have about hundreds of samples in FFT, but thousands, maybe 10,000 of samples in time domain. So what's happening between here?
No, why? When you do an FFT, you take n samples in the time domain.
Okay.
And that converts to n samples in the frequency domain.
But
when you take an n-point FFT, you're essentially taking n points in time, and the result that you get is a vector z1, z0, z1, z2, z3 till zn minus 1.
I understand. But I remember there's an argument in MATLAB function called FFT length. It lets you to specify how long do you want the vector of FFT to be.
That's a function of, that's a function. That's the n. That's capital N.
Oh, I get you.
That's the number of samples that you take.
I take in the time domain.
In the time domain, and that will your FFT will be exactly that sized.
Yes. Thank you.
Wait, I mean, most of the time we set the FFT length to like 512, right?
Correct.
Or like 1024. I think we just lose some information and makes the frequency resolution lower, right?
We'll talk about this. There is a sampling rate and there is a number of samples that you take. We'll talk about this in the next class. But the knob that you have is how many samples you take, which is capital N, and what is your sampling rate, which is what is the time difference between each of these samples.
Yeah. But I mean, in the in Python MATLAB, in the FFT, using the FFT, it should like the FFT isn't as the actual length with as in time domain, right?
Say that again. Sorry.
I I mean, for example, in the time domain, you have endpoints, and however, in the frequency domain, sometimes you just use a fixed number of points to do the FFT.
Oh, that's because
And
you're
in
saying
that-
in the time domain, I have
Yeah.
case samples, but I will only take a part of those samples to do my FFT. That is up to you, how many
Oh.
samples you take.
Oh, so the length must be always the same, right?
Yeah. Your time domain length and your FFT length will always be the same. You can have a long signal, and you can only choose to take this part of the signal, samples from this part of the signal, and use that for your FFT.
Oh, okay. Okay. Oh, that makes sense. Yeah.
Right? If you take 100 samples, your signal might have 10,000 samples. You take 100 samples and you do an FFT, your FFT result will be 100 samples. Your X vector is 100, your Z vector will be 100. If you take more values of that signal, if you say take 500, your Z vector will also be 500. We will talk about this.
Okay. Okay, so what about if you just change the number of vectors, the number of dimensions of the frequency domain? So you're kind of like doing a reduction, right? Kind of doing a dimension reduction, right?
If you change the dimension of the frequency, once you get the Z vector, you project it to some lower dimensional space, you're saying? No, tell me.
Yeah. I mean, I mean, when you're doing this DFT, the frequency domain dimension is the same as the time the time domain's dimension.
Right.
And when you're doing the rotation in a more sparse way, and
yeah,
so you have fewer dimension of the dimension domain.
You project. If you project into some lower dimensional space, you rotate it and you project into some lower dimensional space, you're of course losing information.
Yeah. Okay.
Any other questions?
What was the reason or the intuition that we decided J would be complex?
We just made it up.
We just made it
up. We said that we want to express this stick, and we don't have a good way of expressing it. Man has invented trigonometry, so we can say that this is cos theta, this value is cos theta.
Yes.
This value is cos theta, and we know that this value is sine theta. So we said, why don't we do this to express the state of the stick, or to express the current situation of the stick? We call it as x theta plus some perpendicular direction sine theta. Okay. But we don't know what this perpendicular direction means mathematically. So we invent this new character J. We invent this new character J the same way we had invented this new character negative. Right? Negative gave me a line in the opposite direction. J gives me a perpendicular line. Should not be any different. So once we created J, we said, okay, look, for negative, we had this constraint that if you have minus x, when you add minus x plus x, that should be 0. Right? That was our constraint on negative. Right? So in J, we said, look, if we have J times 1, that means the stick becomes like this. That is J. A stick was 1. This was 1. When you operate J on it, it becomes like this. So that is J. This is the stick J. But when you do J on J, it again rotates and it becomes this, and this becomes a negative 1. And we know what is negative 1. So we can say J squared is negative 1.
Okay, yeah, that's what I was looking for. Okay, yeah. Okay,
but
that makes more sense.
Basically J on J. 1J gives me a 90-degree counterclockwise rotation. J square gives me a 180-degree rotation. But 180 degree is nothing but negative. That we have already defined, right? Look at how math starts with these small abstractions like bricks. and keeps building on those bricks one step at a time. I know negative number, and therefore now I can define rotation.
Okay.
And that gave rise to complex numbers.
Okay, thank you.
Professor, I have a logistics question.
Sure.
So I'm supposed to finish an honors class this semester, and I was just wondering if I could get honors credit in this class by doing some extra work in any way, or maybe something related to like the final project or something in the homeworks.
So for honors credit, do you need it to be a 4 credit, or you don't need it to be a 4 credit?
It doesn't.
Okay.
It
So
doesn't matter.
What do I have to do to give you honors credit?
It depends on the professor. You can choose. Usually professors just give the students a little bit of extra work in any of the areas. So any of the homeworks or final project or anything. Yeah.
If you in one course, if you do something extra, you get an honors.
Yeah.
Or do you have to do extra in multiple courses to get that honors?
No, it's just one course.
Okay.
Yeah.
Ritesh, let me stop the video recording because there's no need to record this conversation. Just put it on for a couple of minutes. And if there is no other question left, then I'll stop the recording and then we can discuss that.
Yeah, that's fine.
Any other questions?
Professor, you talked about Fourier transform and then you mentioned FFT as well somewhere. I just wanted to kind of understand the difference between FFT and the regular transform.
Sure. FFT is saying nothing but FFT is doing DFT very fast. So FFT is a parallelized version of DFT. Does that make sense? Right. So when you look at these operations, these multiplications can be parallelized because you're doing ZM, you're doing Z1, Z0, Z1, Z2, so on till Zn minus 1. And for each of them, you're doing this. For Z0, you're doing this. For Z1, you're doing this. For Z2, you're doing this. For Zn minus 1, you're doing this. So there is lots of computation, lots of multiplication and addition. But it turns out you can parallelize them very nicely and the whole thing becomes fast. And that is what is called FFT, fast Fourier transform.
Got it. Okay.
So it's only a computational gain. You're not doing anything different. You are just figured out a way to do this whole thing fast.
Got it. Okay. Yeah, that makes sense.
Good.
Thanks.
Okay, good. Thanks. Okay, if no other questions, then I'll stop the recording and I'll hang back to see if there's anything.